This is Math 139, Section 2.5, starting in Part A. What we're going to be doing in this section is trying to figure out how we can use the equation of a polynomial function and make some predictions about its graph. We're still going to be needing to rely somewhat on the calculator at this stage. It takes a little bit more higher math, in fact a little bit of calculus, before we're ready to be more specific. But it will be surprising, I think, how much we'll be able to predict about our graphs, even without using our calculator to help. For predicting and understanding graphs, there are really three primary things that we're going to focus on in this class. First of all, the x-intercepts. We already know that we can find x-intercepts by letting y equal to 0. Or we could also think of it as f of x equal to 0. And in the last section, we just finished talking about a bunch of different techniques for solving those equations. The second thing that we're going to focus on is the turning points, or maximum and minimum points. Although we're not quite ready to learn exactly how to find exactly where they are by hand, we will learn to predict their existence, and also their general location. We'll still use a calculator or possibly a computer, Desmos type graph, to actually find them. Lastly, the end behavior. What happens at the end of the graph? Does it go up? Does it go down? What's going on? So three main things to focus on. Finding x-intercepts, figuring out something about their turning points or max-mins, and the end behavior. All right, the first graph we're going to take a look at is the graph of this cubic polynomial, x cubed plus 6x squared minus 4x minus 24. We're supposed to find the x-intercepts by hand, and then we'll talk about how much we can predict before we go to the calculator. So to get the x-intercepts, I set the y, or the f of x, equal to 0. And with 4 terms, I'm hopeful that we're going to be able to get this one by factoring. Grouping's looking pretty good to me, so let's try it. In the first group, I could factor out an x squared, giving us x plus 6. And in the second group, factoring out a negative 4 would also give us x plus 6. X plus 6 is the same in both, so I factor that out. And then I've got x squared minus 4. You can finish factoring that if you want to, or we can get the solutions with the square root method. That's up to you. As long as I'm in factoring mode, I'm going to factor that difference of squares as x plus 2 times x minus 2. So I have 3 separate linear factors. And you'll notice that the section is titled Polynomials that have only linear factors. So that's going to be what's going to happen in this part of 2.5. All right, just because we have a lot to do here, I'm going to start taking some shortcuts. Hopefully you're okay with that by now. If I set x plus 6 equal to 0, we would get negative 6 for a solution. Here I would get negative 2, and here I would get positive 2. Okay. So let me go ahead and plot those x-intercepts. Y is 0 when x is negative 6, also when x is negative 2, and when x is positive 2. So at this stage, I'm going to go ahead and answer the first 2 questions. The degree of my polynomial is 3, and my x-intercepts, negative 6, 0, negative 2, 0, and 2, 0. All right. The next thing we'd like to know is how many turning points, how many maximum and minimum values are there, and also what is the end behavior. We'll use a few examples on the calculator, and I think we're going to learn how to predict that a little bit better even without the calculator. I have gone ahead and the graphs we're going to use in this section I've already typed in, so you don't have to spend time watching me type. So here we go. Our very first one is right here. And notice that's the only one that's highlighted right now. The others aren't highlighted, so it's the only one that's going to graph. I've set a window that's going to work with all of our examples in this section. -8 to 8 for the x, and -120 to +120 for the y, with a scale of 10. I won't change that for any of the examples. So we'll go ahead and say graph. And there we go. Notice that in your notes, I didn't even specify the y values on the y-axis. I just left them blank. That's really not what I'm interested in right now. I'm interested in the shape of the graph. So I'm essentially just going to graph what I see in my picture. Something like that. And if you just want to say our scale was from -120 to 120, just to give you a sense of it, you certainly can. All right, so looking at my graph, I can see that there are two turning points, a maximum and a minimum. If I really wanted to know exactly what the maximum and minimum were, I could, of course, use the calculator to find those. But right now, I'm only asking how many. And then the end behavior. The ends of the graphs go down to the left and up to the right. If you remember back to 2.1 when we were studying power functions, what kind of graphs went down to the left and up to the right? Weren't those the odd powers? They all kind of looked like this. Notice that with a degree of 3, the end behavior corresponds to the same end behavior I would have expected from the graph of y equals x cubed. Right? Up to the right, down to the left. So that's an association we'll want to watch and see if it continues to come true. All right, let's look at a couple more. In example 2, once again, we're supposed to find x-intercepts by hand. So I'm going to let y, or f of x, equal 0 to find the zeros, or x-intercepts, for this polynomial function. Here I only have 3 terms, and it is quadratic form. So I'm going to go ahead and try factoring. X to the 4th should be x squared times x squared. And then I need a sum of -17 and a product of +16. I think -1 and -16 are going to do that. So x squared minus 1, x squared minus 16. Again, I actually could solve right now just by setting x squared equal to 1, taking plus or minus the square root. And the same with the 16. But I'd like to complete this and get all the linear factors. So I'm going to use the difference of squares. X plus 1 times x minus 1. And over here, x plus 4 times x minus 4. That's going to give me x equals -1, x equals +1, x equals -4, and x equals +4. Those are all of the zeros, or x-intercepts. So let's go ahead and put those on there. There are the x-intercepts on my graph. All right. Once again, I've actually already typed this one in. I'm going to go over to the equal sign and hit enter to deselect our first example, and hit enter on this one to select the second. So the graph we're interested in right now is the one that should show. Notice you can clearly see that plus and minus 4 and the plus and minus 1 as the x-intercepts, just like we predicted. And it looks like there's two minimums and a maximum here. So once again, I'm just going to use this as my guide to kind of sketch what I see. Kind of like a rounded off W. All right. This problem has degree 4, so fourth power. The x-intercepts, I'll just jot down here, plus and minus 1, and plus and minus 4, all with 0 as their y values. We just said there were two minimums and a maximum, so a total of 3 turning points on the graph. And my end behavior goes up to the left and also up to the right. Do you remember what types of power functions did that? It was always the even powers, right? X squared, x to the 4th, x to the 6th, that had graphs that looked something like that, with that same end behavior. In this case, since I have a degree of 4, I might think of my end behavior as matching y equals x to the 4th. Right? Has the same end behavior. All right, one more before we summarize. I've got a 5th degree polynomial this time. And once again, I want to start by getting the x-intercepts by hand. So I'll go ahead and say when y is 0, I get this equation. Oops, that's a 45. I'm noticing that I could factor out an x here. Oh, sorry, there's a 4 in front of there. 4x to the 4th minus 45x squared plus 81. And this one's going to take a little bit of work. It's possible that I could use a quadratic form, x to the 4th and x squared. Notice the doubling of the power from the middle to the left. So it's probably quadratic form, and I may be able to factor it. If it's going to factor, I'd have to have a sum of negative 45 and a product of 81 times 4. Is 324. Let's see if we can do anything with that. I'm going to take that 324, and I'm just going to start dividing it by numbers. I know that if I went to 4, it would be 81. 81 and 4 can't be made to add up to 45. 5 wouldn't go in there evenly. Does 6 go in? Yeah, 6 and 54. Still not going to be able to get that to add up to 45, so let's keep going. 7 does not go in evenly. 8 doesn't. 9 and 36. That's got some possibilities. If I make them both negative, we still get a positive 324 as a product, but they do add up to negative 45. So let's go with that. Still got this x out in front. And then I'm going to take this 4x to the 4th, break apart my middle term as negative 9x squared, negative 36x squared, using my numbers, and then the plus 81. Factoring by grouping. First group, I can take out an x squared. And that would give me 4x squared minus 9. And I want to factor out a negative. 36 and 81 are both divisible by 9. That would give me a 4x squared minus 9 also. So I still have the x out in front here. 4x squared minus 9 is a common binomial that I can factor out. And then I'd have x squared minus 9. All right, now we're getting somewhere. Let's continue to factor just a little bit longer. Both of these are a difference of squares. This one would be, 4x would be 2x times 2x, and the negative 9 would be plus 3 times minus 3. And over here, of course, x squared is x times x, and negative 9 again is plus 3 times negative 3. All right, so I have 5 linear factors here. The solutions that this is going to give me are x equals 0. Here I would get a negative 3 divided by 2, and over here a positive 3 divided by 2, and I set those equal to 0. X equals negative 3, and finally x equals positive 3. So, got a lot going on in a fairly short space. Let's see what we can do. 0, negative 3 halves would be negative 1.5, about there. Positive 3 halves, around there. Negative 3, and positive 3. All right, so I already knew this was degree 5. I found my 5 x-intercepts. Let me just list them here. And then we'll go to the graph. I'm going to deselect the second one and select the third one, which is the one that we've just been working with, and graph again. All right, there we go. You can see the 1, 2, 3, 4, 5 times that it crosses the x-axis, which we've already seen. And then it's just sort of that zigzag thing. I'm going to try and sort of draw what I see here. Kind of looks like that. All right, how many turning points do we have on this graph? Well, I see 2 maximum points and 2 minimum points. So a total of 4 turning points. The end behavior, down to the left, up to the right. And again, our suspicions have been it has something to do with the degree. Our degree was 5. And if you think of the power function y equals x to the 5th as an odd power, its graph would have looked something like that. That same end behavior, down to the left and up to the right. So the degree of the polynomial really seems to determine the end behavior of that polynomial. All right, so we know that we've been seeing the same number of x-intercepts, or zeros, as the degree. And we've also determined that the degree tells us something about the end behavior. What about the number of turning points? Let's take another look through these examples. With degree 3, we had 2 turning points. Degree 4, there were 3 turning points. and degree 5, there were 4 turning points. So the pattern so far seems to be that the number of turning points is just 1 less than the degree. Let's summarize all of those observations on the next page. First of all, the number of x-intercepts was equal to n. These are all for degree n polynomials. So whatever the degree, that was how many x-intercepts or zeros I ended up with. The number of turning points was 1 less than the degree, n minus 1. And finally, the end behavior. The end behavior was the same as the end behavior of the power function, y equals x to the n. And those we saw back in 2.1 were pretty easy to predict. All the odds behaved the same way, and all the even powers behaved the same way. So as you can see here, the degree of our polynomial has a great deal to do with what happens when we graph it. It really determines x-intercepts, turning points, and end behavior. Now, something else to keep in mind is that every polynomial that we looked at in this particular part of this section was factorable so that all of our factors were linear, right? Just x to the first power. So far, I'm really only comfortable saying that these are all true if f of x has, I'm going to say, unique linear factors. Okay. Unique meaning there were no multiplicity 2 or multiplicity 3. Linear, meaning everything factored down to an x to the first. There were no x squareds left in the quadratic, or no quadratics rather left in the factored form. Right? We're going to see in the next few sections how those results stay the same or potentially get modified when I start to have repeated factors, factors with more than a multiplicity 1, or nonlinear factors. We'll see how our graphs react.